Okay, good evening, everybody. This evening, I'm going to be going through some of the questions from the exam, particularly the ones that involve doing some calculations and showing you how to get to the correct answers in Excel. I'm going to be focusing primarily on the questions, excuse me, that it looks like people had the most trouble with, so that we're able to get to the questions that were hardest for most people. And with that said, by the way, your results should be available to you within a few days. At which point you'll be able to see which questions you got wrong and what the correct answer was. Obviously, if you have questions about a specific question, you're more than welcome to bring those to either one of the professors during their in-class sessions or during one of our office hour sessions. With that said, I'm going to go ahead and get started. The first question that I'm going to take a look at is question 4, which read, Time Magazine quoted a poll performed in 2008 of 500 Americans in which 8% said that they were vegetarian. Construct a 95% confidence interval for the true population proportion of vegetarians. The lower bound of the confidence interval expressed as a percentage is. Okay, so the first thing that we need to recognize is that what we're doing here is dealing with a proportion. And so we just want to take some time and list out some of the known information. So the proportion is equal to 8% or 0.08. And the sample size is equal to 500. And so then from that, we can calculate the standard error, which is equal to the square root of the proportion times 1 minus the proportion divided by the sample size. And so our standard error there is 0.01. Because we want a 95% confidence interval, we then know that all we need to do is multiply the standard error by 1.96 to get our margin of error. So there we have that. And so then, excuse me, our lower bound is going to be equal to the proportion minus this, which means that our lower bound, the answer for question 4, is 0.056. The next question was to calculate the upper bound. And so the upper bound is simply going to be equal to the proportion plus the margin of error. And so that is 0.103. And so that is the answer to questions 4 and 5. The next question is, can you conclude with 95% confidence that fewer than 10% of Americans were vegetarians? So this is a little bit tricky here. It depends how we round this. With 95% confidence, it does seem that between 5 and 10% of Americans were vegetarians. Assuming that this trailing 378 here does not matter, and we can round to 2 decimal places, which is very common. So if we round to 2 decimal places, it'll be a lot easier to answer this question. The answer is yes. It looks like with 95% confidence, we believe that the population proportion falls between 0.06 and 0.10, all of which is less than 10%. Or actually, I'm sorry. The answer probably, I'm sorry, I'm including 10% in this, but the question is actually, can you conclude with confidence that fewer than 10%, meaning that 10% could not be included in the confidence interval? So because 10% is included in the confidence interval, the answer to this question is no, we cannot conclude that fewer than 10% are vegetarians because 10% is part of our confidence interval. The next question that I'm going to go ahead and tackle is question 7. Question 7 says, this block of 3 questions concerns a U.S. state where the December energy consumption levels for single-family homes had a mean of 1,500 kilowatt hours and a standard deviation of 200 kilowatt hours. So at the very outset, let's go ahead and put our known information here. Our mean is 1,500. Our standard deviation is 200. And we're going to assume that these come from a population of levels that are normally distributed. If a neighborhood consists of 100 houses each, and if we consider each neighborhood to be a random sample from the region, what is the mean and standard deviation of the power consumption of the neighborhoods, or of neighborhoods? So the mean is obviously going to be equal to the mean of the state. The mean of a given neighborhood, we are going to assume is going to be equal to the mean of the state. However, the standard deviation is a parameter for the population. And so what we need to do is turn that standard deviation into a standard error in order to get the correct answer. That standard deviation needs to be divided by the standard error. So we can calculate the standard error. Our n here is equal to 100, which means that our standard deviation, or I'm sorry, our standard error is equal to 200 divided by the square root of our sample size. Now, obviously, if you could do this in your head, the square root of 100 is 10, so then you could just divide 200 by 10. The answer here is 20. And so the standard deviation of a neighborhood would be assumed to be 20. The next question is, what is the probability that power consumption of an individual home exceeded 1,700 kilowatt hours for the month? I'm sorry, I should go back up here so that we still have this information. What is the probability that power consumption of an individual home exceeded 1,700 kilowatt hours for the month? So let me not delete this stuff. We need this information here. So for a single home, we want the probability. So this is going to be equals norm.dist. So we want the probability of 1,700 when the mean is 1,500 for a single individual. So we're going to use the population standard deviation here for a single individual home. And it's true that we want cumulative. And now the question is, what is the probability that the power consumption of an individual home exceeded 1,700? And so we need to take 1 minus this probability, which gives us roughly 0.16, which means that the first answer is the correct answer here. The next question is, what is the probability that the average power consumption of a neighborhood exceeded 1,700 kilowatt hours for the month? And so to get the neighborhood, we need that standard error back. So we're going to calculate our standard error again. It's equal to 200 divided by the square root of our sample size. Also, we know that that is 10. And so now we do equals norm.dist. Our x is 1,700 still. Our mean is still 1,500. But now we're going to use our standard error instead of our standard deviation. And we're going to do true. And then we're going to take 1 minus that. And so Excel is basically rounding that out to 0, which means that the answer here is that the probability is vanishingly small. The probability can never be exactly 0 in these cases. And so when you get a result like 0 or 1 in Excel, then you assume that the probability is approaching negative or approaching 0, meaning that it's incredibly, incredibly small. This probability is probably, got 20 zeros in front of it before there's a number, so Excel just rounds that to a 0 for us. But that answer is most likely not an actual 0. Okay. I'm going to skip most of the true-false questions because the true-false questions don't really typically involve calculations. Those that do involve calculations, I've typically highlighted to go over. You'll also get the correct answer for each of these. And so if you don't understand why a certain answer is correct or incorrect, obviously go back to your lecture notes and to the labs. And if you still don't understand it, then go ahead and stop by one of the office hours and we can go over that with you. Okay, the next question is, an article reports that diastolic blood pressure in healthy adults has a mean of 78 millimeters with a standard deviation of 6 millimeters. So let's start out here, mean 78, standard deviation 6. Assuming the diastolic blood pressure is normally distributed, what percentage of individuals are expected to have values between 78 plus or minus 6 millimeters Hg? Choose the most accurate answer. What we need to recognize here, to easily get the answer to this, what you can recognize here is that the margin of error that we're looking at is equal to the standard deviation. When the margin of error is equal to the standard deviation, that means that the z-score that you're multiplying it by is 1. If the z-score that you're multiplying it by is 1, then that means that you're going out 1 standard deviation. And so a quick way to answer this, if you look at it and pick this up immediately, is we're going only 1 standard deviation above and below the mean. And if you remember the rules, 1 standard deviation above and below the mean contains 68% of the sample. However, if you don't remember that, then you can solve the question another way. So what you need to do is figure out so we can do equals norm dot inv, norm dot s dot inv. Oh, I'm sorry, excuse me. So we're gonna do norm.dist, and we're gonna just do 78 plus 6. You could also calculate that out, but you can type these things right into Excel, which makes it nice and simple. 78, standard deviation is 6, true. And then we're gonna do the same thing. 78 minus 6, mean of 78, standard deviation of 6, true for cumulative, and then we're going to subtract those two things. And what we get, not surprisingly, is 0.68. So there are two ways to solve this one. You can do it sort of conceptually and in your head, knowing that this is exactly 1 standard deviation above and below, and when you go only 1 standard deviation above and below the mean, you have exactly 68% of your sample there. If you don't recognize that, then you can do it this way. You do norm.dist, you test the value, the upper value with a cumulative distribution. You test the lower value with the cumulative distribution, you subtract the two from each other, and then you get 0.68 as well. The next question, I believe, is also in reference to this. Use the mean and standard deviation given of diastolic blood pressures above, and assume that diastolic blood pressure is normally distributed in this population. What is the percentage of samples of size equals n that are expected to have values between 78 plus or minus 6? Choose the most accurate answer. So here we need to turn our standard deviation into a standard error. So standard error is going to be equal to the standard deviation divided by the square root of 9, which is our sample size. In this case, I'm just going to type it out. Square root of 9 is 3. So our standard error is 2. So here we're going to do equals norm.dist. Our x now is 78 plus 6 again, comma, 78, comma, standard error of 2, comma, true, and equals norm.dist. Our x now is 78 minus 6, 78, our standard error of 2, true, and then we're going to subtract the first one from the second one from the first one, the lower one from the higher one, and we get 0.99. So 68% of individuals are expected to have a blood pressure in this range. 99% of samples of 9 people are expected to have a mean value in this range. And we've talked about this before, that you're a lot more likely to get a mean value that's closer to the population mean, a sample mean value that's closer to the population mean than an individual's value that's closer to the population mean. And that's because with one individual, there's higher probability that they're in the tails. As the more and more individuals you collect, the lower the probability is that multiple people are that far away from the mean. All right, now suppose that the study had reported that the mean diastolic blood pressure of healthy adults is 78 with a standard error of 6. So we had already calculated the standard error from the standard deviation in the previous question and got 2. Now the information that we're being given, no standard deviation, but a standard error of 6. They don't mention sample size. Assume that diastolic blood pressure is normally distributed in this population. What percentage of individuals are expected to have values between 78 plus and minus 6 millimeters, excuse me. So the problem here, and I imagine this might have taken you some time to sit here and think about whether or not you could solve this. The answer is that you cannot solve this. There is not enough information to answer this question. With a standard error of 6, we cannot solve for both of the unknowns in this problem. We have 2 unknowns in this problem. We don't know the sample size, and we don't know the population standard deviation. If we knew one of those and the standard error, we could solve for the other. So if we knew the standard error and the sample size, we could multiply the standard error by the square root of the sample size to get the standard deviation. Alternatively, if we knew the standard deviation, we could utilize that to get to the sample size. However, because we have 2 unknowns in this problem, we don't know the standard deviation. In this case, this is not given to us. This is given to us as 6. So we don't know the sample size and we don't know the standard deviation. There's no way to figure out the answer to this. Okay. In an air pollution study, the Environmental Protection Agency technician obtains a measure of 4 micrograms of suspended benzene soluble matter per cubic meter with a standard deviation of 1 microgram per cubic meter for a sample size of n equals 16. So, excuse me, let's go ahead and just quickly type out the information that we know. Mean is 4. SD is 1. N is 16. So what we need to do, what we might as well do, is calculate our standard error. It's going to be equal to the standard deviation divided by the square root of the n. Notice that a lot of times in here we're giving you perfect squares, and so 16 is a perfect square. The square root of 16 is 4. 4 squared is 16. Perfect squares are any number where you get a whole number when you take the square root of them. 16 is one of them. 10 or 100 is a good example of them. 25 is an example of them. 5 squared is 25. 6 squared is 36, et cetera, et cetera. So oftentimes you don't really need to do the math to take the square root of these. I can just divide this by 4 because I know the square root of 16 is 4. If you didn't know that, you could, of course, type in the Excel function for square root here. So our standard error is 0.25. So what we need to do is construct a 95% confidence interval for this mean. So the lower bound, so we know that 1.96 is the value that we needed. If we didn't know that 1.96 was the value that we needed, I show you in the tutorials how to calculate those proportions. So if it's not 95%, and you don't remember that you don't remember that 1.96 is that critical value there, there are ways that you can use an Excel function to calculate that. I'm going to skip that step because we should know that 1.96 is what we need. And so then all we need to do is calculate our margin of error, which is equal to 1.96 times the standard error. It's 0.49. And so then our lower bound is simply going to be equal to the mean minus our margin of error, 3.51. And our upper bound is going to be equal to our mean plus our margin of error, 4.49. So in general, the 95% confidence interval for this sample of 16 is 3.5 to 4.5. And so that is all the questions that I had highlighted as being problematic for a lot of individuals in the class. There are a couple of essay questions that we haven't fully graded yet. And of course, if people still have questions by next week, I'm more than happy to go over those more in depth during my tutorial next week. And like I said, if you do have lingering questions, once you get a copy of your exam and you can see how you did, feel free to schedule some time in somebody's office hours to talk more about those questions or bring them up during class. Thank you so much and have a good night.